Hello, welcome back. We continue with the microcorruption series. Today we're gonna be dealing with the signing verification challenge. Before we start diving into the challenge, so the challenge name is Cold Lake. So before diving into the challenge itself, we should be, I think, starting first to introduce the concept of signing in cryptography before we start solving the challenge. Yeah. So we go with usual sketch AO. So the concept of signing stuff, guys, is really important in cryptography and in security in general. It's a kind of way that we can um, it's a kind of way that we can use to verify the integrity of the stuff on the internet. For example, let's suppose there is a person A and there is a person B. And A wants to send something to B. So let's say, for example, he want to send X. So what is the thing that we can, what is the thing, or how can we, here's the problem. How can we verify that X was not changed along the way? This is the question that rises, or the problem that we have in our hands. Um, so to solve such problem, guys, we introduce something called signing. So to sign something, for example, is to make sure that the sender, to make sure that you know the sender of the message. In our case, it's X. So when B gets the message X, it should be verifying the integrity of the message. So to make sure that we can send something, for example, over the internet, and make sure that that our message uh, does not get changed, we should make sure, for example, that we sign the message. So to sign a message, we can use signatures, and we have to use this time asymmetric encryption instead of using symmetric encryption in the previous challenge in Baku, if you remember, if you watched the video. So asymmetric encryption is based on two keys. The first is the public key, and the other one is the private key. So here's how the signature process is done. So basically, A will be sending two things. He will be sending the message, and he will be sending a signature. So then B will get those two things, which are the message and the signature, and should find or should check the integrity of the message before trying to deal with it, just to make sure that the sender is A is not it's not someone else who got in the middle and changed the content of the message. So this is how stuff got done. So now let's go back to the process of how the signature got generated. So for example, I won't go into too much details about how the signature got generated, but I want to just explain one fact, that since we have two keys, which are the key 1 and the key 2, this is a private key, and this is a public key. In the case of signature verification, we will be using the public key to verify the signature that we will be sending, and we will be using the private key to sign the messages for the receiver. How are we going to be doing that? We will be using the private key and the public key. So, for example, let's suppose. So, for example, um, let's suppose HP has some kind of program that she want to execute on her devices, and let's suppose the program is a bootloader. So for example, this bootloader should be executing only code that was generated by HP. It won't be, for example, executing some code that you, for example, have written, or I don't know, another company or someone else. So to do that, she have to generate two keys, which one of them is obviously the private key, and the private key should be protected from everyone else. Otherwise, for example, if I got the private key of HP, I could, for example, sign my own code, my own custom code, and run it on the bootloader, for example. And the public key should be, for example, hard coded on the device to make sure that the public key can verify any signature given to the device. So, for example, the verification of signature or the verify function should be taking the public key and should be taken also the message. Just an example. So it will be taking these two and return either true or false, for example. True means that the verification is cool. False means that the verification has been um, has failed actually. Yeah. So this is basically how the verify function works. Now, what's really interesting about this thing or about the verify and the verification in general is that like that we can make sure the integrity of any kind of message that we have sent. So this is basically how the verification is working. We actually have a lot of signature verification, let's say techniques. One of them we will be trying to see here in this challenge is the ED250 5519, which is actually based on a concept called elliptic curves. You can check them out if you want. You can read about them in crypto hack if you want to. Just it's basically this is the signature verification that we will be using. Okay, I think it's time to check the challenge. So we go the usual flow. We try first to just as usual just run the code that we have in our hands and then try to do some static analysis on the code that we have. So before we do that, I think we should be writing the notes. Yes, so what do we have? So overview, log ID all is under new management. The log has been put together from bits of leftover scrap from the old factory. Details, so the log ID to blah 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 blah. So what do we have? So to support rapid development cycles, this log accepts a program from the old password input prompt. The program must be signed by look ITL, so engineering aren't concerned it will be used maliciously. There are two programs, one of which is below in hex format and is used in the factory to test proper lock operation. The other program not reproduced here is restricted and only available internally at locid all. So this is the load address of the program. This is the program text, which is the program that the CPU will be executing, and this is the signature of the manufacturer. Okay, so I think we will be needing those informations later on. We can just copy that into our notepad and see what we can do after that. Okay, so this is a good sign. We already have some kind of example that is signed, which means that this is the program, this is the signature, and this is the load address. We will see what this load address is exactly later on. Okay, so I think we should be cool now. Let's just go try to now just run the program. Yeah. So what do we have in here? So please enter the second stage load address. Let's just try this out. You can just try his example. Um, what do we have? So this is a program, and this is the signature. Load address outside allowed range of that. It's not in the range. Okay, so that means that the loading address that we have gave is not in that range. Okay, interesting. I think we should be having something in the range. So that means I think maybe the since the Indianists have a lot to do with that, I think because of the Indianists, for example, we have written 100 8000, I'm sorry. Instead of writing 8000, I think it should be swapped. The byte should be swapped since it's a little Indian architecture. So yeah, I think it's supposed to be like that. If we try to continue, yes, so this is the program in hexadecimal. This is the signature. Let me just get the signature in one line. Yeah, and now we give this signature. So yes, it is the same. It is the same. Yeah, we actually got that code executed, so he gave us access denied, which is a good sign. Now I think it is time, guys, to just do some static analysis in the code, just understand what those functions are doing exactly, the usual stuff that we do with any kind of micro-corruption challenge that we have. Um, yeah, so let's see. So we start with the main. So what do we have? Um, the basic stack alignment that we always see. We have also move. Welcome to the skewer bootloader. So this is just a simple message, excluding the first byte at the stack pointer, at the offsets pointed to by the stack pointer. We also have another message, okay, and then he's doing some stuff. So he's getting some string. So this therefore will be containing the size. Um, so this is the size. This should be the place, the loading address, load address. Let's say offset is better. So this is load offset, load address offset. The 2 bytes that we give at the first login. So he will be reading 2 bytes. Then we have please enter the second stage program. So this is the place where we read the program itself. So he will be um, reading, um, he's not reading here, wait a second. So he is just entering the second stage program. Since there is a memory set, he's initializing the memory. So he will be initializing 0x101 bytes. And then he's gonna be, this is actually the source. He, he will be initializing them. Um, let's see, he's gonna be initializing them with zeros. Yeah, so this therefore equals to 0x0. Since this is supposed to be the destination, which is register 15. So register 15 equals to register 15 plus 0x43, which means that he's changing the place where he's gonna be putting these zeros. So he's gonna be writing 0x101, which is, I believe this is in decimal 257, yeah, which are 257 bytes of zeros. He's gonna be writing into this address. Yeah. So now calling the memory memset or memory set with those values. So we have the destination, which is register 15. We have also register 14, and we will be initializing 257 bytes of data into this location, just filling them with zeros. Then we start reading some input. So basically, I suppose this is where we write or where we read the second stage program, the program itself, the code that will be executed on the device. So register 14 is gonna be equal to 0x100. Um, just reading, just reading bytes. Now register 15 should be equals to make. This is basically the location or the destination. Register 15, we do the same thing. Register 15 equals to register 15 plus 0x43, which is the same place that we have initialized with zeros. Just now we get the string with the register 15 um, with the 0x100, which are 256 bytes. So we need 256 bytes of data. Now we need to enter the signature. So again, he's initializing some data, but this time he is so register 15 with the 0x41. So this is just initializing uh, initializing for signature. We can just go back for here and just divide this block like that. Let's just separate them together. I think this is better, just for me to understand and for you to understand too. So this is just initializing, initializing space for the program. Yeah. So this is initializing for program. This is initializing for the signature. What do we have now? So we finish it with that. We finish it with that. Now I think it's time to go see the other line. So now he's reading the signature, and then he is moving the first byte and the stack pointer. The first byte should be um, actually the first two bytes actually should be the loading address that we have that we have read in the first stage, or in the second stage. I'm sorry. Yeah, it's the same thing. Actually, they all of them are second stage. Yes, so it's supposed to be, so register 15 is supposed to be the loading address where we have loaded the program. So the loading address is where we have loaded the program, and then we give the program itself, and then um, we actually we actually read the signature. Yeah. So the first thing is we give the place where we want the code to be loaded. The second thing is we give the code that we will be loading. And the third step is to give the signature of this code that we want to execute. Yes, so he's gonna be testing if the register 15 is not 0, I suppose, or 0 or whatever it is. So he will be jumping if it's greater or equal, obviously, than 0. So if it is greater or equal, then he will be jumping to the current address plus 0x8. Which we can tell, just we don't have to debug pretty much this few lines of code, because they are just doing some checks on the range that we have seen. And since we already have the range hard coded, we don't have to just go through all of that. We can just know where this gonna be stopping. Yeah, so I suppose this is the block where he's gonna be checking. So this is just to check that the load address is in the range, this range. Yeah, we don't have to go pretty much too deep. Now if everything is cool, if everything is cool, we should be jumping into this block. Yeah. So what do we have in here? If everything is cool, we jump in here, and we actually start now copying something. So it's memory copy. So we will be copying 0x100, which are 256 bytes. Just to copy. We will be copying from the register 14, which is already pointing to register 14, which is equals to what exactly? Register 14 should be equal to this address, which is stack pointer, which is the stack pointer plus this value. Yeah. This is actually gonna be the source, which is the program that we have already gave. You can check that, for example, when just we can go back. Yes, as you can see, this is where we have read the stage program. And as you can see now, I can just check that by using, as you can see, he's just moved the stack pointer into the register 15, then added it to the register 15 0x43, which is now the offset where we will be writing our program. Now, what's really interesting in here is that he is moving, or he is passing down this address as a source. So this is a source address. Now, the question here, we miss one argument, which is the destination. So the destination should be in the register 15, which already have the loading address. So register 15 is having the loading address. So that means that now he's gonna be loading the program uh, to the loading address. So he's gonna be loading the program into the offset that we have gave in the first stage, or I'm sorry, in the second stage program. Yeah. So we gave him already the loading address where we want to load the program, and we give the program, then we give the signature, and the loading address should be in this range. So for example, if we gave him just 8,000, it should be cool, and then we can give a program, and he's gonna be copying our code into memory. Now let's see what's gonna be happening. So he's moving again the stack pointer, and then he is incrementing the register 12 with 2, and then he is moving now another variable, which is um, just register 13. I suppose this is a size. Yeah, I suppose this is a size. I don't know yet what those two are doing exactly. Register 14 should be equals to what's in the stack, which is the loading address. And register 15 is having some kind of address. I suppose we should check that out, what this 2400 is having exactly. Yeah, so it's having those values. So register 15, I suppose, should be the key, or actually the public key, to verify the signature. Why am I assuming that this is the public key, guys? It's simply because, as you can see, it's just a bunch of bytes in hexadecimal, and the verification of ED25519 should be done using the public key, and any kind of verification of signature should be done by the public key. So we should be passing on the public key. So to do the verification, we are passing down the public key, we are passing down the loading address of the program. Let's say the offset of the program now is better, the offset of the program, and then we are passing down the size of the data that we will be checking on. And we pass also, this is actually register 12 is containing the stack pointer. So the first 2 bytes of the stack pointer are the loading address. If we add +2, we actually get to this signature. We can check that if we want. As you can see, to read the signature, we have passed down the stack pointer, and then we incremented the register 15 with 2. We can just do that. For example, register 15 is containing sp plus 2, stack pointer plus 2, and register 15 should be equals to the stack pointer. So as you can see in this one, we have the stack pointer pointed to by the register 15, and if we add 2, and if we add 2 to it, we actually get to another 2 bytes. So basically, to get to the signature for the verification, um, we should have to take what's in the stack pointer and add 2 to it to get to this signature offset. So to do the verification, um, we have to give the public key. We have to give the public key. We have to give the offset of the program, and we have to give the size, which is equal to 0x100, which is equal to 256, and we should also give the signature of the program. Okay, this is for the verification. Now, once we do that, we compare with one. We compare the resistor 15 with 1, and if it is equal to 0, then incorrect signature, and we go back again. We jump back again to the first stage. Otherwise, signature is valid and we will be executing the payload. Once we execute the payload, as you can see, he will be executing what's in the stack pointer +2. So obviously he will be trying to execute the program that we have in our hands, which is, as you can see, this one. Yeah, so let's try now to let's try now. So this is executing the code, and then testing is gonna be testing something. If it is equal to 0, then he's gonna be jumping to access denied. If it's not 0, then he's gonna be giving us access granted and open up the lock for us. Now, just to summarize what we have did in here, if we take just a little look back and try to summarize what we have did, let's just try to summarize that at the end. So basically, we um we give the address of the program to load. Then we give the program that we want to execute. Then we give the signature of the program that we want to execute. Now once we do that, we have only these three stages, I'm sorry. Um, so basically, he gave us already just one case that we can use, which is this case. He already gave us a loading address. He already gave us a program text, and he already gave us something that has a signature. Well, the first idea that can came in your mind is we just have to write a code that can open up the door, inject it in the bootloader, and then try to sign that code using the private key, and then just get the code executed inside of the device. But the problem here with this idea is that we don't have the private key. We only have this program that is already signed, and we should be trying to craft something maybe that have something to relate with this program. So here's the idea. So the idea is to create a program that can be executed by this program. So the first thing to do is, how are we gonna be understanding what this program is doing just from the bytes? We have to disassemble that, reverse engineer back what this program is doing, then try to find a way um, to open up the door. Just this is simply what we have to do. So the first step is to go just and try to disassemble this. So there is already a disassembler in the microcorruption interface. We don't have to use anything from the internet. So if we give this and we try to disassemble that, as we can see, so what this program is doing, it's moving this address um, into the register 5, and the MBR is gonna be branching to the register 5, means that it's gonna be jumping to this register 5, which means it's gonna be jumping into this address. Now we just taking a look at the other just registers. It's just doing the same thing, and then it is clearing the register 15 and then it's returning. Now, nothing special about all of that. But I think we can just play around this place. As you can see, this address is in the range of the program loader, so we can load stuff to this address. So here's the idea: we will be loading some program into this address, and then we will be, since he does not check whether the program can be malicious or not. This is the first thing, and the second thing, after loading any kind of program, he does not check the signature before loading the program. He checks the signature of the program after loading the program itself in the memory, and the other thing, he does not flash the memory after loading a program, which means if we try to craft something into this address, and even with giving a false signature, or let's say a wrong signature, it's gonna be theirs. It won't be deleted from the memory, and it won't be flashed, because this is the way he implements his logic, actually, which is somehow vulnerable to this attack. So we can just, I think, now try to figure out some malicious program, something that we can craft in order to open up the door, and then we can just have to we just have to call this program that's gonna be redirecting the execution, or the execution of the program, into another place, which is our code, which will be located at this address. So here's the step that we will be doing. Step um, step to solve. First, inject some code at the address 8008 with with the program that can open up the door. Second thing is to call the program code, or the signed program code that he gave us, to redirect the execution to our code. So this is the two steps that we have. Now the challenging part is how are we gonna be crafting something that can open up the door. So the first idea that can came in your mind is just by going back to the code a little, is that we can just create something that can just jump directly to this address, which gonna be obviously opening up the door for us. This is the first idea that can came in your mind. But another idea could be just to simply, instead of returning is 0, we should be just trying to change the status of the register, which is the SR. Actually, we can change just the SR in order for the test to be not 0 to jump to this block, which we can do obviously just using the assembler just directly. For example, let's move just for example FF0, for example, this value into the SR. Um, this is the this is actually the assembled object that we can send. So just by executing this, we can actually just move this value into the SR, which is not 0, which will be obviously granting that this jump, if 0 is not going to be taken, which will be executing this code. Now another thing to mention here is that after doing that, since there is a call, obviously, since there is a call in here, we should be returning from this, let's let's just say stack frame. Let's suppose we want to just return from this stack frame. So to do that, we should be doing a return. But the problem here is that when you do a return is not, it cannot be assembled. And if you check the code, you can see that in the above, the first two lines of the source code is that we have the return implemented the address 0010, which means that if we branch into this address, we should be able to return. So we can just do a simple BR there. So if we BR into the address 0x 0010, we should be cool. Now the thing is that the problem with this code is that the BR, if we try, for example, to disassemble that, just we have assembled that, and we try to disassemble that, it's not giving us the BR, the branch to that address. So to do that, we just have to do that manually. We just have to find a BR and see how it's implemented, and then change the value of the address that's gonna be jumping to. We have where is just I can just use BR. Yes. So it's using those bytes, and if I'm seeing that right, we have, as you can see, to flip the bytes that we're gonna be jumping to. So we can just take that and try to disassemble that. So is that one. So if we change the values, for example, to 00 or 10 0, since we have to swap them together, um, disassemble. I'm sorry. So yes. So this is the values that we have. Now, if we go back into this one, now we combine this together. We combine those with those. What do we have? So this is for just moving um 0xFF00 into the statute register, and this is for moving or just for branching to the address of the return that we have at the beginning of the code. So just using this two, we should be disassembling that and getting the piece of code that is correct. Now we try to just chain them together. Disassemble. So this is the program that I will be executing. So let's try to execute this code. So we have to reset the device first. So we will be loading into 8008 if I'm not wrong. Let me just check that. Yes, it's 08, but we have to give it in little Indian format, so we have to just flip them together again. We flip the bytes, and then we have to give the program. So I want to execute this program, and then I want to let's send whatever signature wrong that can be. For example, this one. Now I wanted to also see. Now we are gonna be now he since it's an incorrect signature, we cannot be executing that code directly. So we wait a second. And let's try to see if the code that we have gave is already loaded or not. So the code is starting with E32, I suppose, and it should be going on with a stack pointer. Where is it exactly? Let's see. So this is the public key. Um, mm, what does the stack pointer is ham42 A E? Hmm. Yes, we should be. Yes, it should be here. Yeah. So it's loaded in here. As you can see, this is the code that we have written. It's just loaded at the offset that we wanted to, which is 8008. This is 8008, and as you can see, this is the program that we have loaded. Now it's time I think to get his program. Let's try to write his program into another offset away from the offset that we have choose. We can just, for example, choose 990. We can just write that here, and the program is gonna be his program. That's gonna be jumping obviously to our offset that we have, which is 808, and we give his valid signature, which will make him execute his code. Now we should be hitting the breakpoint now. Yes, we have hit the breakpoint. Now let's try to see if the 1990, so this is his code. that ends with 41 and that begins with 35. So this is 35, this is 41, so this is his code. Now, I think if we step one step, we start executing the code. So he's executing the code, obviously. So he's moving the offset of our malicious program that's gonna be opening the door into the register 5. Then he's gonna be branching to the register 5. Then he's gonna be moving now. Now he's starting executing the program that we wrote. And as you can see, the state to register has been changed. Now we return and we open and the door is unlocked. Now this is an interesting challenge, to be honest. We just have to solve now that with the right stuff that we have. So it's gonna be 0880. We will be giving this program, and then we will be giving whatever signature we want, and then we give the program that he have. Let's suppose I want to be writing that to 1990, and then we give program, and then we give the valid signature that we have. A good challenge, to be honest. I really loved Cold Lake. I really enjoyed just solving that. I hope you two enjoyed that too. Yes, so this is all about signature verification. I hope you learned nothing, something new. And yes, I think we hit the end of the video. So don't forget to subscribe. Don't forget to just follow me on Twitter if you want. You can hit me on Discord if you have any kind of questions. And yeah, have a nice day. Bye.